let's record. So, okay, for the record, this is going to be a very informal and very loose introduction to the subject of topological design and topology optimization. Okay, very participatory session. Let me see, which screen am I sharing? Am I sharing the right screen with you online?
Yeah, we see the presentation, yeah.
Presenter view, let me share the right screen. Okay, now you have it, right?
Yeah.
Okay. So this idea, according to many people, goes back to the year 2003, but I've also found papers as old as 1996 or something talking about this idea that apparently it has been even well known at that time. But this one is arguably one of the most famous papers from Bencho and Sigmund from the, Denmark Technical University, DTU. So they popularized the idea of topology optimization. The very term topology optimization can be a little bit confusing, so I will dig into the meaning of this term because it's actually more than just optimizing a topology. It's also about discovery of a shape and discovering a design. Whether that's necessarily the answer to our question or not, that's another point. That is the point of talking about topological design as well as topological optimization or topology optimization. But just to start properly, if you already know that you're going to design a truss for a certain load case, that's a term. So why are we building that bridge? Because we want to make an icon to make a name for ourselves, or we want to let people pass from one side to another. That second one means that there will be a load case on this bridge. And conventionally, architects starts from the idea that I know how to make a bridge. I'm going to make a truss structure, and it can even be potentially this complete truss. And if this is given, for whatever reason, if you think this is given, then maybe you can think about, okay, what's a reasonable thing to do? Reasonable in the sense of this thought experiment. A colleague of mine who was a little bit grumpy actually gave a very good definition of what is engineering. He said, if you give unlimited money and unlimited steel and concrete to anybody on the street, anybody can make a bridge. So that's not so special, right? They will make it very, very strong, right? Unlimited money, unlimited concrete, and unlimited steel, right? So the art of engineering could be said to be about reducing the amount of materials or resources necessary to build something given a desired level of functionality and a use case here, right? So with the same functionality, the same load case, etc., can we change the sizes of these elements to achieve the same thing? Achieving the same thing would be to, is it a good word to say, to not to comply, but to make something that can let the forces be efficiently transferred to the ground, because the structure is not supposed to fight the forces. So we can say, loosely speaking, that the structure is supposed to work for that load case, right? And the load case is the assumed weight of all the people walking on it or going by bike or whatever. So this was one. So size optimization from a given topology or a configuration of the structure as a bunch of beams, struts, whatever, connected to each other as a truss. The second one being the architect had a dream last night and thought that maybe we can make the bridge like this. So this shape we consider as given. This topology we consider as given, that this is going to be a rectangle with so many holes. And then the only question left to be answered is what should be exactly the shape of these holes. Not so interesting, in my opinion, not from this point of view, but maybe from the point of view of topological design, we can make it interesting by discretizing this space. Because the shape of these individual elements is a rather ill-defined question. I find it an ill-defined question. But okay, this one, here's where people get confused. So when we talk about this one as so this is a bit magical, right? So you have just a beam full of materials and you want to, frankly, you want to discover the design, right? And yet we call it topology optimization. So why do we call it topology optimization? This is a very rudimentary introduction. I want to dig deep into this term. And I want to tell you as a starting point that not only in this process we discover the topology, but actually as a free bonus point, we get the shape out of this magically. That's the whole point, right? So, okay, before going further, let me try to clarify this point here. So what you have the other thing here. Okay, maybe I can draw on the screen. It's even better. Okay, so let's say this is our so-called design domain. So the domain in which we can have any amount of material that we want. And if we, no.
We see it, Piers, before we saw it. We were sharing it.
The whiteboard?
Yeah. Yeah, now we see it.
Oh, now it's a problem with the...
Sorry, is it okay? My internet connection is lagging from time to time if I switch off the camera, so maybe I can hear you better.
Absolutely, yes. Yes.
I just wanted to... Okay.
Good. Okay, I was sharing the wrong screen. Okay, so let's say this is our material domain. We are going to form a structure. And before I go further, typically in this line of work, we use the term form for a combination of topology and shape. Topology is purely about topology or graph or connectivity structure, and shape is the shape geometry, right? And the question is, why do we call it topology optimization, or what do we mean by topological design or topology optimization? I may have explained a part of this for some of you, so there will be a little bit of repetition, but I think it's a good idea to make sure that we are all on the same page. For the same reason that I can, let's say, pixelate anything like a shape of a bird. What a horrible drawing. Okay. I can pixelate. Jesus. Okay. I was supposed to be good at it, but it's the mouse, right? I can blame the mouse because I'm drawing with it. You can pixelate this shape, right? So if we are okay with a low resolution, then we can draw with on the pixels and get a shape as a pixelated shape. And I'm not going to be bothered by it. You may not like it, but I think I'm going to be fine with this. Whatever. It looks like a dog, but okay. Yeah, as a bird. So this question of shape can be discretized. So I think this is our starting point, discretization, which opens a very interesting door. This shape is discrete, and we also know for a fact that we can only do discrete simulations on a digital computer. So if we are going to make a structure that is a little bit jagged in its form, and it's discrete, even literally discrete, like to be made up of bricks or some kind of blocks, then the tempting question is, okay, if we want to, let's say, think of this as a structure, it is a structure, right? This animal has some bones and it's standing on its feet, right? And so if you think of it as a structure, we can analyze it as a structure. So how would you analyze this as a structure? With finite elements, right? Or something finite or something discrete, finite elements, finite element method, finite difference method, discrete element methods, and a whole bunch of such methods. These are methods in general for solving numerical, for numerical solutions to, these are called numerical methods, but usually people don't say for what, method of doing what. So these are numerical methods for solving the so-called partial differential equations. So what is a partial differential equation? What is a differential equation? The rate of change of something is typically mathematically described as a differential. And if the rate of change of something corresponds to something else, or something depends on the rate of change of something else, then you have a differential equation. So for instance, I know for a fact that this is the most, perhaps not the most famous differential equation, but it's the one that has stuck to my mind. The rate of change of a population, the growth of a population depends on the rate of change of growth of a population depends on the population itself, right? And this is a positive feedback loop. And some colonies of bacteria, if you have a Petri dish, the kind of thing that the biologists use. My knowledge of biology is really, really poor, below zero. But okay, if you have a Petri dish and you have a culture of bacteria on this Petri dish, and you manage to make it an isolated system, then the bacteria start eating each other and producing some poison that will affect the rate of change of the rate of growth in their own population. A differential equation, right? But a partial differential equation. So differentials are written with these kind of notations, the Leibniz notation, for instance, rate of change of something over time. So let's say population over time should be in principle proportionate to the population itself. That's the first one I just talked about, right? So, but these are typically functions of single variables, but in our line of work, we are dealing with functions of at least 3 variables, which are the spatial variables, X, Y, and Z, right? Therefore, we get these kind of equations starting with partial derivatives, this sign that looks like a letter in the Russian alphabet, but it's not a Russian letter. It's called partial in English, which is for partial derivatives. So partial derivative of, let's say, temperature shown with U over X. So how much does temperature change when we go from here to here, for instance? How much does temperature change when we go from here to here? That will be partial differential of U over Y, etc., right? So I start with temperature because temperature can be a scalar field. The forces and so on, they are vector fields. That story is a little bit more involved and complicated. We'll get to that as well. But okay, so the big picture is that if you want to solve these equations are typically mostly formulated in 18th century or sometime around that time by people like Carl Friedrich Gauss, by Leibniz and great mathematicians of those times, and they are usually formulated referring to the so-called continuum or a continuous space. So this notion depends on a notion of an infinitesimal change in the direction of X. But infinitesimal, which is like as small as you want to be, like it's kind of the counterpart of the infinity, as big as you want to be. Those things do not exist in digital computers. But we have a small change over an element, and we can have a large number for infinity, but that will not be infinity, right? So the general idea would be to discretize these equations or even write new equations in a purely discrete form about these elements to be able to simulate the behavior of a system under some inputs and some so-called boundary conditions, right? So some of the boundary conditions may be that, for instance, these ones are fixed to the ground and they cannot move in at least not in the direction of y, right? And other sorts of boundary conditions, not my cup of tea, like rotational restriction for some nodes, etc. Yeah. So boundary conditions on the displacement of these nodes, right? Okay, but I think I'm losing the big picture here. So the big picture here is that, okay, whatever we want to do with these simulations for figuring out how this system is going to work is going to be based on these discrete elements. So the tempting question is the following. So if we can do these simulations on the discrete field here, the discretized domain, and after every round of simulation, we can do what we can call an aggregation of something that we care about. For instance, referring to this particular example, structures, we can potentially be concerned about the rigidity of this structure, which might be hard to measure. But an easier way towards optimization would be to think about something negative that we want to minimize, like some form of what we metaphorically call an energy in the system, but not energy as in the energy put into radiators, and energy in the sense of a cost that we want to minimize. So I will get into that notion soon enough. And then we want to minimize that energy. So the tempting question is the following. We can simulate this whole thing as if this is our design, right? And then figure out, okay, how terrible is the design as it is, right? In terms of that notion of cost or energy. And then we can figure out if we have that as an equation, which part of this design is responsible for this being so terrible, like the most responsible part. By removing which we can make everything a little bit better, the whole thing a little bit better, right? Then we can take that, the top worst or the worst of the worst, and then we redo the simulation and then find the next worst one and then redo the simulation, find the next worst one and remove them until we reach a bottom line level of the volume, which can be a constraint of validity here because otherwise the whole thing disappears, right? So it might be more efficient to not have this structure at all, right? Because if there's no structure, there will be no cost, no energy, nothing whatsoever. So we will keep that as a constraint, okay? Okay, so but what is the whole idea of why the name topology optimization? So if we start removing some stuff, so let's say there is a load case here, which is to support these, well, not support, what's the perfect term for this? To exert these forces and let the structure handle them and conduct them to the ground, let's say. Not to fight them, but to, yeah. So let's say, ideally, I mean, I kind of know this intuitively, but we are going to probably find out that this part is doing almost nothing and this part's not so much, etc. We're going to remove a bunch of this stuff and we're going to maybe find this structure, sort of. But we are not going to directly find this part. So let's say we have removed this bunch of things, right? And have reached our volume. What we are going to find is the following. So we're going to find that these elements apparently were not so terrible in our evaluations, so they can stay. And these ones had to be removed, right? So what we have found at the first look, if you ask me, is that this and since all our drawings are topological, I hope you don't mind the lines being so shaky and ugly, right? Because it doesn't really matter. So what we have actually found is a subgraph of a supergraph. So we could have had these points, these nodes in the graph as well. There could have been these links as well, right? So it's kind of like from this complete picture, we have chosen this partial picture. So from a supergraph, we have chosen a subgraph. So if we do it properly, there are some complications. I'm oversimplifying some parts, but if we do it properly, we can be focused all the time on the nodes, or actually I should say elements, referring to the idea of finite element method. In this case, they look like nodes, and figure out which elements are the most unnecessary or the ones responsible for raising the cost so much. By removing which, we can make everything better. But effectively what we are doing, so if every element here corresponds to a node in our system or a node in our graph, in our supergraph, by removing some of those nodes, effectively we have also removed some of the links. We have found this subgraph. We have found a topology. But this topology, interestingly enough, by virtue of the so-called Poincare duality, corresponds to these nodes being present. All of them. So we have also found a shape because these actually happen to have a shape. They do have a shape, right? So we do have a shape, and even in the pictures that you normally see for referring to topology optimization, they're very smooth and very crazy shapes. This is how they're generated, right? So voxel by voxel or cell by cell. These cells, there is no theoretical reason for these cells to be like voxels. That's very important. That has to do with the idea of duality between tessellations. Could have been this one. And these connectivity graphs describing the connectivity between the cells. This is a tessellation in 2 dimensions. Agreed? Because this can be some sort of a, what do you call it? Origami. Yeah, crease lines. And the equivalent of this in 3D will be a polyhedral tessellation. This is a polygonal tessellation, in this case with triangles. Mm-hmm. Of not using voxels. Yeah. Oh, that would be in topological design. I will get to that. But what will be the advantage of using voxels? Let's talk about that one now. Yeah. So let's first talk about the advantage of using voxels, and then we can talk about the advantage of not using voxels. Right? So the advantage of using voxels, that's a great question. For topology optimization is that, well, arguably this is the most familiar tessellation of a 3D space, which is the least biased towards any any shape that we may have in our mind. And without getting so negative about this bias, because that bias might be actually exactly the thing that we need in the next part, which is topological design, because we may actually have a preference towards these shapes if our material is not, what is the right word, isotropic? If our material doesn't work the same way in compression or tension. Yes. So if it is isotropic, then it works. We expect it to work in the same way in all directions, right? But if our material is not such as such, we may actually have a lot of compelling reasons for not starting from such a tessellation, right? That raises the importance of topological design before thinking about topological optimization. Yeah, the so-called shape functions might be somewhat complex for unfamiliar elemental shapes. So you have elements and you need to run some form of a numerical simulation of a partial differential equation. And for the well-known shapes like prisms and voxels and triangles and quadrilaterals on the plane, etc., you have the so-called shape functions in some textbooks pre-computed for you. So you just implement them in your code and you get your finite element model, sort of. But the more complex those shapes, the more complex that business is going to be. But there might be compelling advantages that may even force us to ignore those issues and go for something else. Because after all, we might not be working with finite element method, we might be working with something else. So my point is that we are going to do some evaluation of a cost function, of an energy function, energy as in cost, some sort of a bad energy, like evil energy, right? That we want to minimize. And the most important aspect of this is that we want to model that energy or cost or whatever, evil spirit or whatever, as a function of some decision variables. These decision variables being typically shown by the letter X for decision variable, and a long list of them on a blackboard or on a whiteboard. I would put an underline to indicate that this is a vector. In a mathematical typesetting environment like LaTeX or Word, you use bold letters for vectors, right? Bold lowercase for vectors. This is a bold letter X for a vector of decision variables. So guess what? What will be the decision variables? The decision variables are these to be or not to be decisions for each and every one of these voxels. Is this really necessary? Is this really necessary? Is this really necessary? So we're going to ask this question so many times, right? And then if it turns out that one of these decision variables, which corresponds to the existence or the absence of this particular cell, is going to show us a high sensitivity in that energy, evil energy or cost or whatever, to the existence of this guy here, then that's a compelling reason for removing that from the equation, right? So I'm trying to keep it general because this idea of discovering a design is not particularly attached to the structural mechanics, or this can be any domain in physics. So it can be thermodynamics, it can be geometric optics, it can be acoustics. If the big question is this, can we relate this notion of functionality or the opposite of functionality, which is some sort of a cost for this, to the existence or to the presence or absence of each and every elemental cell in this spatial domain? If we can do that, then we can have some form of topology optimization. Shall I recapitulate? So We want to have a cost function or an evaluation mechanism that can accept as inputs however we do it. It can be from thermodynamics, optics, whatever. As an input, it should be able to accept a vector of decision variables whose elements are indexed so many others and indexed with reference to these elements. So for the time being, I'm thinking about this vector as a vector in the space of let's first do the other one. The two numbers 0 and 1 to the power of n being the number of elements. Why to the power? This is not power as in raising like 2 to the power of 10. Right? This is a notation for referring to the Cartesian product of sets, which means that any vector here is a combination of numbers coming from this set and a combination of n items as such, right? So a tuple of 10 such numbers coming from this set, right? So this part perfectly describes in a necessary and sufficient way what is this vector x, what could be this vector. So it's a bunch of zeros and ones. An interesting fact, if you put a monkey behind the typewriter who can type zeros and ones, right? And write a vector like this, or the monkey writes a vector like this, for every vector as such, you have what? You have a design, right? So if our only goal in generative design was to generate a design, even the monkey can do it with one button, right? That's a very important one because every vector in this form corresponds to a design. It might be a terrible design, it might be a good design, but it is a design. Makes sense? Because of this discretization. But then an important question is, this is a one-dimensional list. This is a two-dimensional or even possibly three-dimensional. So how do we know which is which? We might have a very basic form of remembering which is which, a very good way of remembering which is which. Whatever way we have to remember which is okay as long as we're being consistent. But some of these ways of remembering which is which are advantageous because they are globally accurate in the sense of their completeness. The idea is that we want to make a long list of indices or addresses for the elements. A list is going to be one-dimensional, right? And in a consistent way. So one of these beautiful and consistent ways is called Morton order for voxels. Morton is the name of the guy who came up with this idea. The idea is the following. So imagine we have only 4 voxels. So the first one is on the 0, 0 in a two-dimensional world. So if this one is the coordinate dimension of x, this is the dimension y, I would assign these 2 coordinates to this cell. This one, let's say here is 1. This one is 1 and 0. Yeah, right? What would be the coordinates of this pixel? 1 and 0. This one, 1 and 1. This one will be, what will it be? 0 and 1. So Morton said, okay, let's concatenate these 2 coordinates or weave these coordinates and make numbers in this form. 0, 0 for this one. 1, 0 for this one. 1, 1 for this one, and 0, 1 for this one. What do they remind you of? Binary numbers. So in binary numbers, so this represents 2 to the power 0, 2 to the power 1. So in binary format, actually this equals these numbers in decimal format. This is 0, this is going to be 2, this is going to be 1, and this is going to be 3. How does this describe an order? Well, obviously 0, 1, 2, 3, right? So that makes a so-called zcurve. In this case, it looks like n because I'm not using image coordinates, I'm using literal, let's say geographical or geometric coordinates. Typically, when people do it on image coordinates are, annoyingly enough, they start from the top left corner of a screen. So don't get confused. So I think y in the image coordinates is, okay, y in the image coordinates goes down from the left corner of the screen and x goes to the right. But they start counting from the top left corner, which is a little bit annoying. But because most of these stuff that you can find online are coming from computer graphics with a lot of obsession with images, then that could be the case, and therefore it will look like Z instead of N. In this case, it looks like N order, but this is famously known as a Z order or Morton order. So this is one way of doing this properly if you have voxels or pixels, right? So you can imagine that if you do this for any number of points, you will only have ones and zeros, and they will always translate to decimal numbers, and they will always give you a curve that looks like a snake. So it will visit every location in your space, and you have a long list of one-dimensional indices that you have made out of weaving these two coordinates. And that makes this decision variable as a vector.
What would be the name of the third?
If you had a voxel here?
Yeah.
Ah, okay, I'm cheating a little bit because first okay, good that you asked this. So the coordinates of this one will be 2. So first you make these coordinates binary in themselves because they are integer coordinates in voxel. Then you weave them together. You interleave them together. Good that you asked. Okay. So in this case, they were already binary, but if they're not binary, so you first they have to be integer coordinates. So this only works for voxels and pixels because voxels are in fact points in the world of Z as a set of integer numbers to the power 3, the power being the indicator of the Cartesian product of sets, yeah. Which is a fancy way of saying that voxels are basically points with ijk coordinates, all of which are all of which belong to the set of integers 0, -1, -2, +2, etc. Right? Okay, so this means that if you have a monkey behind the button, that monkey can generate a design. Okay, that might be a little bit offensive for some people, but this is what it is, right? So even a monkey can design. So then the next question is, what will be a good design, right? The constraint of volume not disappearing completely, the volume being less than or more, yeah, less than or equal to something, and we don't go less than that, right? Or more than or equal to something, so we don't let it disappear, right? That can be simply checked by just adding all the decision variables. If they add up to some number that is large enough, that would be acceptable as a design. The less material, the more likely it is to be efficient, because the more likely it is to have a lower cost, right? But for only looking at validity, we can just check it by adding these numbers here, right? validity in terms of minimum volume. I'm talking about a very, very general and simplified formulation of this problem. And I would like to keep it general because this idea goes beyond structural mechanics and this particular way of solving it or using finite element method also. Okay, so now we know what a discrete domain can do for us. It has the amazing advantage that we can discover this shape. Let me use a distinct color that I haven't used so far. A very thick line. We effectively discovered this shape. I mean, this is the crudest form of describing this shape. Oh, I should have done it like this. Okay, whatever. This was part of the design also. Okay, so this is the crudest way of doing this. Let me redo this. Okay. These ways of, let's say, vectorizing or finding the dual of this shape or finding the level sets around this bunch of cells or the more fancy word would be for them an isosurface. Is something separate from this story. I have explained that already in a lecture yesterday for another course. I will soon upload a video about that. That story of finding a fancier version of this, which would be basically about finding these borders inside these kind of cells, which can be a little bit more fancy and more fluid, right? But essentially it's about finding a border that separates the cells that meet a certain condition and the cells that do not meet a certain condition. This condition is now Boolean. So they're either in the design or they're out of the design, right? But for mathematical reasons, in topology optimization, it's common to work not only with these crisp or Boolean values, 0 and 1, and work with values ranging from 0 to 1. Or actually not even ranging from 0 to 1, but ranging from a minimum so-called density. I'm running out of space here. So some sort of an x minimum to 1, and the x minimum larger than 0. So the x sub I, referring to that element, is supposed to be in between some x minimum and the number 1. The reason for this is numerical stability of the optimization algorithms. With zeros, with exactly 0, they may get crazy, okay? And solving this with only integer variables, that might be more difficult or easier, depending on how you look at this as an optimization problem. Some optimization packages are actually prepared to work with integer decision variables. Some, or the larger category is capable of dealing with continuous variables. So having these as continuous variables, even though our question is a crisp question, can have advantages for the optimization mechanisms that we can use. And then even if this is a float variable floating between some number close to 0, a very small number, and 1, not exactly 0, but whatever that is, you're going to get some kind of a ghost of this design with those values, because they're not going to be like perfectly either turned on or turned off. Some of them are going to be a little bit shady, right? Then again, you can define a level set and say, give me all the ones above, I don't know, 0.75 density. And then again, you can get a level set, and then again, you get your design. And one of the most common methods for getting those kind of isosurfaces is marching cubes if you're working with voxels. If you're not working with voxels, then we have to use another method, or maybe we don't even need to use another method to find a smooth surface, because maybe this is our design already. If you're going to build it out of these blocks, this is our design, end of story. No reason to smoothen it or do anything else with it. This is our design. That's a big deal, right? The one for getting smooth shapes, marching cubes. That's the one I've explained in another lecture. But in general, these methods are methods for forming isosurfaces or level sets in 3-dimensional domains. Another one is called dual contouring. Another one, marching tetrahedrons. That's the one I've implemented myself. So that's the one I know in absolute detail. Okay. But whatever those things are, if our design is supposed to be discrete, if you're not bothered by that discreteness, we already are looking at it. Right? Imagine we had these magnetic boxes, we could build this as a design with them. Right? Okay, so this is getting a little bit cluttered. So anything else that I have to talk about on this picture? Okay, guess I can. I have saved it. Okay, clear. Okay. So far, so good. Okay, so now let us reflect on this question. What could be topological design? So let's first reflect on this one. So let's see if this is general enough. Given a natural topology of a regular tessellation of a 3D space, such as a voxelated space, what would be the natural topology for voxelated space? The connectivity between the voxels, right? How can an optimal shape topology, I keep them as a pair because given any topology like a subgraph, you can immediately see a shape, right? As the halo or the border or the isosurface around that bunch of nodes, right? Be found for a given objective function, which is some sort of a cost, which is a function of decision variables that we already looked at. The decision variables corresponding to the presence or absence of the cells in the final configuration. This presence and absence can also be a value ranging between 0 and 1. Yeah, like a ghost, which is 60% present in this room or not, right? Okay. So subject to some inequality constraints of validity. So what would be one of those inequality constraints? Like the volume, please not disappear, right? So let's keep a few of these boxes in space. Otherwise, having no design is the best thing for the environment because that means no cost whatsoever, right? Whatever that cost may be, right? Examples can be heat sinks or coils from a thermodynamics point of view, or structures from a mechanical point of view, mechanical efficiency, right? We have also solved one such problem from an optogeometric point of view. For instance, light and what could be the best possible shape for a building with respect to daylight. So this is something that we already looked at, right? So we started from a natural or rather regular or whatever simple topology for the space. Now if and we can also think about combinations, of course, right? There was no mathematical reason to start from that regular and perfectly regular topology. In fact, in a program like ANSYS or COMSOL, sometimes you start from a tessellation of the space that is not so regular. So for historical reasons, numerical reasons, whatever, they may prefer to start from a tetrahedralized or triangulated domain. And they do the same kind of operation. Then the question, the to be or not to be question for every single element will be a to be or not to be question for, do I really want to have this triangle in my design or not, right? For every single triangle. Or for every single tetrahedral element. Reminder, what are tetrahedrons? They're not pyramids. They are these packages of milk or sorbetto ice cream in four-sided volumes, right? Okay, they're the equivalent of triangles in 3D, okay? Okay, so now let's think about this. So given a non-trivial topology describing non-trivial, so this one is going to be made up of some, let's say, some interesting tessellation of 3D polyhedrons, tessellating or partitioning or tiling. So these terms are somewhat interchangeable. A three-dimensional domain, which may or may not look like a box. It's a three-dimensional domain. So we partition it into a bunch of non-trivially shaped, but piecewise linear. That's normally an assumption. Piecewise linear, which means faceted polyhedrons, right? Nothing so fancy and blobby in the shape. We form a 3D tessellation or tiling of the 3D domain represented then as a supergraph describing a lattice. How can a form that is already found, a form found design, be approximated as a topology or subgraph in that topology? And you see that I'm using the word topology as if this can be an object, and that is exactly correct. In the same sense that we can refer to this object being a geometry, we can also refer to a superset as a topology, right? A topology. What is a topology? Reminder from the lecture about topology. It's basically a superset describing a collection describing a bunch of sets that can have relations with each other, relations in the form of intersections and unions, such that the intersections and unions are also included in the collection. All possible intersections and unions are accounted for in the collection. So we don't have isolated things. We don't have unaccounted connections or unions that are not accounted for in the collection. That is a topology. I can go back to that definition in a minute. Actually, I will do that just to be clear. But okay, so it is a collection of connectors, combinatorial connectors, like links, like faces that connect the nodes to each other. Simply put, we can think about it as a graph for the time being. A graph or a hypergraph. So it's a different representation of the same thing, the collection, but essentially the information content of a graph is topological. So you saw the graph in the other picture, the connectivity between the nodes in whatever sense of connectivity. In this sense, it was the connectivity in the sense of neighborhood by virtue of sharing faces, right? Graphs are much more general than that, but in this case, this is literally about a tessellation in space, and sharing faces with each other would be a very good reason to consider them to be connected, right? And form found designed to be approximated as a topology subgraph in that topology. Okay, so what on earth am I talking about here? Remember our paper about How do I get that thingy back here? Any idea? Ah. So remember our paper about these space filling polyhedrons used for approximating a shell? It is not the only way of doing this, but it gives a complete example. Did I mess it up? Yes. Okay, so these kind of things are because of such visual similarities are actually called honeycombs or lattices. The kind of lattices that you get or the kind of graphs that describe the connectivity between some space filling polyhedrons or polygons. In this case, I'm drawing on a two-dimensional domain and I don't have much time or patience with this little mouse. So I'm drawing a bunch of space filling polygons. So they're filling a two-dimensional space. And now let's say I have a design. I'm not going to check my skills for drawing birds and stuff, but let's say this is too large for approximating this. But okay, if I give you a thought experiment, then I think you will be fine with that thought experiment. Let's say we are trapped in a castle made up of stone. So I'm just trying to relax your mind about what these tessellations can be. And we have some half an hour to escape the castle. Otherwise, a monster in the castle is going to cook us for dinner, right? Okay. We are putting our minds together to find a way to escape the castle, and we are trying to make a hole in the wall without dying in the process, of course, right? And this is a very thick wall made up of stones. We want to find a way out of the castle. So if you have ever dug a tunnel under the earth, etc., you know that it should have some sort of a shape like this, right? So we take this idea, we implement it here. So whichever stone here has an intersection with this must be preserved so that the thing doesn't collapse. So let's say I intersected this one over our heads, and then we can remove these ones and we can get out of the castle, right? This is the idea of the approximation, which is an approximation that is topologically correct, right? So you could argue that this is a good approximation of that imaginary arch, right? What would be the equivalent of this in 3D? Instead of this being a curve, this would be, that's where it gets a little bit tricky. Yeah, we might want to work with it as a surface, but I wouldn't do that, because if I wanted to do this in 3D, the game would be like, think about this as a snake that cannot go from one polygon to another polygon without being detected. It has to pass through the border of the polygon, right? What is the dimensionality of the intersection between a curve and a polyhedron as such? It is either going to be a point or no point. It either does intersect with one of the facets of the polyhedron or it does not. So let's say these polyhedrons are made up of soap bubbles, and if the snake hits the soap bubble, boom, right? It disappears, right? So it either hits or it doesn't, right? If I wanted to intersect the snake with an object like this one, you can see it in the ceiling. It's a lattice already, right? So the sneaky snake can go through this lattice somewhere without even touching one of those things ever, right? So imagine doing this in computer graphics would be insane, you know, trying to find the intersection of a curve in the middle of this stuff, especially if you want to detect that, right? But if I want to detect the intersection between two elements in a three-dimensional space, those two elements should have dual dimensionality with each other. Dual in the sense of Poincare duality. So if one of them is one-dimensional, the other one should be n minus one-dimensional. N in this case is 3 because n in this case is 2. Therefore, the other one should also be one-dimensional. The other one should be an edge in one of these polygons. Edge, not the polygon itself as a surface, right? This space as a whole is two-dimensional. Poincare duality tells us that there is a pairing or duality between n minus k dimensional elements and k dimensional elements in a space like Rn. Yeah. So if our object is the sneaky snake, which is one-dimensional, arguably because the length of a snake is more than the diameter of the snake. That's why we call them snakes. You look at them, you immediately tell, oh, a snake, right? How do you say if it's a snake? Because it's obviously a one-dimensional creature, right? Okay. Ignoring its thickness, of course. Yeah. Then the pairing is between a curve and an edge in this two-dimensional picture. So if you go to a three-dimensional picture, what would be the pairing? A snake, one-dimensional object, k being 1, this n being 3. That means we should be looking for two-dimensional objects, not one-dimensional objects. Is that clear? Because the likelihood of this snake actually hitting one of these surfaces is much more, or actually that's the one we can find. The other one is even technically going to be impossible. Two curves in the middle of nowhere, you know. The intersection, they're actually zero-dimensional both, supposedly from a mathematical point of view, they're both zero-dimensional. So what's the point of looking for the intersection? Then we fall into these issues of numerical precision, etc. And let's not forget that we are not dealing with real numbers in digital computers. What are we dealing with? Floats. Floats are not real numbers. So we always have a truncated precision. So whenever we try to do things geometrically, we are on a very dangerous path because whatever we're going to do is going to be prone to numerical errors because our numbers are not exact. Yeah. So the main advantage of doing things topologically is that we get away from those kind of situations as much as possible. So this was a very non-trivial example, but this shows you that in fact, from a mathematical point of view, there is no reason to think about only this kind of lattices or this kind of tessellations or tilings. It can be any other tiling that you can come up with, any other tiling that you can argue that would be better than the other tiling, which was the normal tiling. What's wrong with this tiling for approximating these kind of shapes? It may easily correspond to these kind of situations where you have when you make this with these magnetic voxels, it might be okay. But basically here you're at if you're standing on this, you're at the mercy of the gooiness or the strength of the glue between these two. And that's exactly what we don't want to have in masonry architecture because our glues are not far from super glue, right? So we are not going to rely on any sort of tensile strength, right? So there's a fundamental flaw here, right? And that was the reason and is the reason and would be the reason to go and search for this kind of other non-trivial tessellations that can allow for passing the forces from one to another more efficiently without compressive forces, shall we say? Is that acceptable? Stress, yeah. But since we are talking about structures that are actually supposed to work in equilibrium, I think we can also safely talk about force without talking about stress. But because whenever I mention the word stress, I get stressed because the reason why we should be thinking about stress is that probably we are going to do some sort of a crime, which is using materials in bending. That means inefficiency. So if we are here today, that's because we're going to build structures that only work in compression or in tension. The structures that only work in tension are known as tensegrity, I think, invented by, what was his name? Buckminster Fuller, yeah? Or no, not tensegrity. These structures that are made with cloths. How do you call them? Membranes. Yeah. They, yeah, tensegrity is a combination. So these membranes, yeah, the membrane structures are supposed to work only in tension, right? So from that theoretical point of view, they're also interesting for us. But now we are looking at the opposite sort of structures. We are which are supposed to work only in compression. Okay. And what was I saying? Oh yeah. So because we are working with structures that only have such forces, we can work with force densities and force and equilibrium of forces. So one of the other methods that we can use is force density method. And for form finding of these shapes, we can use dynamic relaxation. That's the one I've explained in detail. This is the one I can explain to you in as much detail as you want. And the truss network analysis by Philip Bloch. And this is really old. I don't remember who has first come up with this idea. This is invented in 1970s by a researcher by the name of Sheck. I know the paper by heart, but I don't recall his first name, right? A method of form finding. So you take something of this shape, not of this shape, with this topology, something that can find a relaxed form for itself. Let's say a rope, whether it's on the ground, on the table, or hung from 2 points, it has the same topology, right? The connectivity in the rope stays the same. What Gaudi did not change the topology of the chain network. He hung these chains already chained together from some points, and they found a relaxed form for themselves. So all these methods, you could say, well, at least these two, find a relaxed form for the chain network or some form of a cable network. And that's why I asked you, what would you call that thing, which is the equivalent of this, or the analogous of this chain or this rope in 3D? I would not go with a surface. For lots of numerical, computational, and topological reasons, I would actually go with something that I would call crochet embroidery. If you have ever been to Belgium, you have seen these artworks, kind of like non-trivial knitting patterns, and make these flowery-like things. It's not a cloth, it's some sort of a artwork with akin to knitting. I wanted to do some sort of artwork, but I created yet another mathematical object. But you know what it is roughly? You have seen it? Some form of knitting, but without making a surface. It's full of holes, right? So if I were to offer a name for that, I would say, let's work with that. Why do I not call it a fishnet? Because a fishnet has a non-trivial topology, which is typically just warps and wefts in 2 directions, that's all. But a crochet embroidery, a piece of crochet embroidery has usually this non-trivial or interesting topology.
The manufacturing how do you, because I would describe that as solely shape optimization.
Yes, it is definitely. Yeah. So the idea is that we accept the topology of this. Well, we accept it, but we have designed this topology ourselves. But once after we have designed this topology for the thing that is supposed to be relaxed, then we accept it. Then we just find the form. So that's why I'm saying form-found design. But even in this design, there can already be a topological design, which is the tessellation design of that thing. So this can get very, very interesting in multiple ways. So one of the ways this can get interesting is that this pattern can actually be already the dual of our cell configuration in this domain. Or have some reciprocity with this, have some sort of correspondence with it. This is one way. The other way this can get very interesting is figuring out which other ways can we use to tessellate a given domain in 2D. So this one would be the first one I would start with, thinking like a carpenter. How would I make a gabled roof? Because whatever we are going to do is going to be similar to finding a vault-like ceiling, which can arguably have the same DNA as a gabled roof. So I would start from this one. I would start tessellating this further, or subdividing this tessellation further and further, using an algorithm, for instance, like Catmull-Clark subdivision. And then I would form a bunch of blocks. Or first I would form this sort of a crochet embroidery here out of this tessellation pattern. And then I can look at the dual or the dual cells or the cells already configured using by this subdivision. And I can crawl them towards the apex points or the points of high altitude. Could be these two in this case. Sorry. Or I can think of many more non-trivial tessellations for this. So we can get very creative, and this is not an exact science. In fact, the works of a researcher from Block Research Group, Dr. Robin Oval, are the things that we use in this line of work for exploring the different topologies here. From a grammatical point of view, graph grammars, etc. What are the different ways we can tessellate this given domain? And as he has shown beautifully in his work, then with each topology there can be a corresponding level of functionality. And some topologies arguably work better than the other topologies, because whatever topology we put here for the crochet or the chain network, we will relax it like Gaudi, but not as a physical chain network. We will relax it using these methods computationally. We find the shape, even given the acceptable force densities of our material, using this one. We find the exact shape at which we are sure that this is going to work as a relaxed shape, and then we can approximate it with these blocks, and then we can find out, okay, what's the total cost of having this? I mean, cost in that case, in the former case, was something that we can call compliance. In this case, yeah, maybe something similar to that can be developed. Notion of cost for the discrete element model that can describe this bunch of blocks approximating this. That would be the reason to think about discrete element modeling. If we cannot do that, I would do the same good old and terrible approximation that we used, which was to simplify this as a truss-like structure, deluding ourselves into thinking that this is actually a truss. We knew that we were doing something wrong, But that was the only thing we afforded to do back then because we didn't have 25,000 euros to buy the software application for dynamic, for discrete element modeling. So we assume that this is a truss made up of these elements like nodes and struts. And we approximated the functionality of this as a truss and using a finite element method, right? Can put weights on these weights, the self weight of these blocks on the nodes, and assume some sort of strengths for the connections in between, etc., etc. Yeah. Where was I? How can a proper cell subdivision tiling be designed as a design space? Okay, for a problem. Yeah, and then the other way this can get very interesting is this cell subdivision not being so regular like this, not so being so irregular like this one, like the castle, being something reasonably regular where it needs to be regular, and having a shape with this idea in mind that we want to have a good flow of forces to the ground as quickly as possible. And the cantilevers are the things that we want to avoid as much as possible. So we can embed all these things into the genome of this lattice, because realizing that whatever we do with this crochet embroidery, etc., is going to end up with one approximation here as a shape. Yeah. So we will always get the shape out of, this is what I forgot to mention, a coloring of the supergraph. So the supergraph is there. All possible connections are mentioned here. Let's say this is the supergraph. It's a supergraph, right? Connectivity between these cells. So we can say that this notion of design that we're talking about is actually equal to coloring a graph. So we say that, okay, this one in. So again, a monkey behind the typewriter can just push a button and get a design. That design might be horrible, but it will be a design. So the problem of designing the shape is only handled once, in fact, which is in the design of this lattice here. So if we have a list of zeros and ones here, or black and white for the coloring of the nodes, it's basically a two coloring of that supergraph. Every design is a two coloring of that graph, which is a fancy way of saying that it's a vector of ones and zeros. Right? So this definition doesn't yet satisfy me because it's not general enough yet, because it didn't include the case of actually generating the topology of this lattice from this tessellation. That would be a different case. But assuming that we are all looking for solutions that can work everywhere and can make a complete building. So I think the idea of having a lattice that can, a tessellation, a complete tessellation that can encompass the entirety of a building would be more interesting, somewhat more interesting. Because we are after architectural solutions that can not only make one vault, they can also make something that you may not call a vault, like a structure, a masonry structure that supports a staircase, for instance. That is also part of a volume, right? A big volume in space, right? Makes sense? So given a configuration of a bunch of floor levels connected with a bunch of ramps and stairs and stuff like that, the question would be how to find a masonry shape It was also the question in the other approach. In the other approach, we try to discover a shape from a very neutral, very regular grid, assuming even regularity and an isotropic behavior in the material. Yeah. In this case, if we have a low resolution approach, maybe we can think about this as a matter of first designing this non-trivial lattice, which could be good both for approximating these shapes, the vault-like shapes, and also good for the other question. So that's what I meant by combining the two. Is there any reason that you can think of for not being able to do the other thing on this grid? Any like fundamental reason? Everything we said about the other approach can also work here as well, right? Again, provided we can evaluate some notion of cost or something on as a function of this being a decision variable, then we are in business again. We can try to discover what would be the best shape if this is our entire domain. But if we are trapped in this castle and we are just trying to get out as quickly as possible, we don't have too much time for the simulation, then we probably start from this idea, this good old idea of making an arch. We start with this given idea for the design, then we approximate it, and then we get out before we get cooked by the monster. Okay. Shall we have a coffee break? Or even call it a day? I don't know. I want to also tell you a little bit about the math behind this, but maybe we can postpone it to another moment if it's getting very...
Well, from my side, I can keep going a bit more.
Yeah.
I don't know.
Yeah, same here.
Yeah, okay. How about you? Oh. Hmm? Yeah. Yeah, let's grab something to drink and then get back to it like in 5 minutes or so. Yeah.
Yeah, all right.
Sounds good.
I put
Record.
on the record. Okay. So
So do I understand correctly that your advice is kind of not advice, but that it is a possibility to sort of merge the two options, the non-trivial typology and the natural typology, sort of not, yeah, since we are trying to find a shape, but also like an ergonomic shape and structurally possible shape, let's say. So do you think it's wise to sort of look into both and sort of find if you can use bits and pieces of both types, like to create a lattice to which you work with? Or would you just stick from one or the other, like the regular voxel 3D space and then this more like a 3D tessellation?
yeah, so I think among you all, so you're all in the Gothic group, so you all have the question of finding a masonry only or an unreinforced masonry shape, an efficient one. So the process of shape optimization is definitely interesting for all of you to understand as a prerequisite for understanding the other one. So actually topological design is much more intuitive as a beginner to start with, and shape optimization in general, because topology is given. And the simulations are more approachable because those simulations that I mentioned here, they're all for the systems that do not have the stressful factor of having stress inside. They're all about forces, right? And so you can maybe start from there. Maybe you can even end there, even for those of you who are working on topology optimization, like Inglu and Khan. Maybe you can even start from these, repeatedly do the same simulation, get an answer, right? I'm oversimplifying some of the technical details in the story, but yeah, that would be an interesting combination. For the other ones who, I think most of you are working on it from a design point of view, because you have bigger fish to fry somewhere else, which is the completeness of the solution for being capable of realizing all kinds of architectural configurations. So, and that question is a very tough one, in a sense. That would be something that you can help the others with. And so this back and forth discussion, I think, would be very helpful for both sides, actually. For the side of topology optimization per se, we have only two toponauts. Actually, I've invented a word. Do you know about the word astronaut? So the United States of America calls their space men and women, they call them astronauts, right? The former Soviet Union called their space men and women, they call them, guess what, cosmonauts, right? And the People's Republic of China calls their space men and women taikonauts. Did you know that? So this apparently in Mandarin is similar to a word that means some sort of space. Yeah. And cosmos in Russian apparently sounds like space. And astros in Greek sounds like space. And the second part is nautis, from like aeronautics comes from in Greek. I'm trying to transliterate Greek here. Yeah. So the words are always combinations of these two. So my proposal for the Genesis lab is to call our explorers topo nodes. Exactly, because the second part is always the Greek part, and topos is already a Greek word. So I think we have a very compelling reason to call all of you explorers, topological explorers, toponauts, right? Perfect word, right? I can even write you the Greek one. So let me see. I think this is Omicron, which is acceptable. Let me do my best. And this is new. I hope that Anastasia will not be disappointed. Upsilon and tau, something like that. Whatever. I'll check it later. Yeah, exactly. So we established this term. From now on, you're all toponauts, right? Okay. So where were we? Okay. A little bit about did you have another connection in mind, Leticia?
No, I was just wondering your take on like mixing the two approaches and when it's more meaningful or the other, but no, thanks for the explanation.
Okay, sure. So let's dig a little bit into one of these notions of the evil energies or costs, right? So this is the most famous one from a paper or the book by Differential and Sigmund, which is the following. So there is, where do I start? So this is the thing that you are trying to minimize, which is called compliance. If the object in question was just a spring, you squeeze it, you push it, it complies and it gets shorter. You pull it, it complies, it gets longer. So it stretches. Stretching it or squeezing it would actually mean to cause quite a lot of strain in the system. But this system is supposed to be behaving in an elastic way within of course a range, right? So if you're being reasonable with that spring, then it's going to behave in a linear way. If you push it too far or squeeze it too much or stretch it too much, then it will go into the plastic mode, and that is this stress strain relation, which is maybe for most materials around us up to a certain level, it's linear or can be assumed to be linear, and after a point which is called the yielding point, it yields and it becomes, oh, actually I should have drawn it like this, right? The strain goes up in a nonlinear way, right? So this epsilon is usually reserved for strain, correct? And sigma, the lowercase sigma, is reserved for stress. So now we're getting into the stressful subjects, which are full of the notion of stress, because these notations have emerged, historically speaking, from a context where everything is done with isotropic materials, see, and finite element method being the method of solving the equations for these isotropic materials. And the stress is something that you didn't have when you were studying in high school. If you have had any sort of physics or mechanics, you probably didn't hear about the word stress. You have probably heard about it in structural design, right? Because you have to go through that sort of stress. But the other ones who have only had like structural mechanics in high school, they have probably only seen the so-called free body diagrams. So you have a force exerted to an object, maybe another force, etc., and the object is supposed to be behaving as if it is just a single node, right? The box in on the slope rings a bell. It has a weight, and on the slope it will have a an acceleration proportionate to, I don't know, m mass times g, the acceleration of gravity acceleration times sine of theta or something like that, you know, that sort of story. So these are all based on the so-called free body diagrams, which kind of disregard the dimensionality of the object and the volumetric dimension of the object, and assume that all the forces are exerted to a node, right? This is the kind of simplification we also had to make to delude ourselves into thinking that that object was a truss. So we reduce every cell into a node, and we reduce every connection into a strut between the nodes. Anyhow, but if you're really stressed about what are the stresses inside a high dimensional element, like a 2-dimensional element, or a 3-dimensional element like a cube, then the stress and strain are not going to be 1-dimensional anymore. You're going to have stress, let's say, in 2 directions or 2 degrees of freedom. That's a very important notion. So you can consider nodes, not the kind of nodes that we love to work with, the topological nodes, but thinking the topological node, let's say, is this one, which is the representative of this entire element as a picture element, as a 2-dimensional picture element or a pixel. Now, if we are really thinking about it as a structure element, then we should also worry about the stresses in 2 directions and the strains in 2 directions and the combinations of them. Yeah. So the notation, the typical notation for them is the epsilon in the direction of x, epsilon in the direction of y, and I think the typical notation for the combined is gamma for x and y, gamma for, I think that would be the one for two-dimensional system. Yeah. And you have to relate them to the stresses. In some way. There's a matrix that can relate it to two in terms of some partial derivatives. I don't want to go there yet, okay? Or maybe never. Let me delete this page. Oops. Okay. But let's get back to this idea. I think this is a very important notion here. The notion that we are looking at here is very similar in a very tempting way to something that we call the Dirichlet energy. So Dirichlet is the name of a mathematician or physicist who first formulated this. Dirichlet energy, it's okay. I don't want to write the math because I'm sure I'm going to make a couple of mistakes. So let me just explain it in a very loose way. I can also cheat a little bit and look at it from Wikipedia, but a long story short, if you have a system consisted of so many springs, for instance, and imagine that all of these springs in the system are somewhat uncomfortable because somebody is pulling them apart where they don't want to be so far apart, and somewhere someone is pulling them, squeezing them where they don't want to be squeezed, etc. For all kinds of reasons, they're all to some degree uncomfortable, right? The total amount of discomfort in this system if you write that down, it will take a form like 1/2 of some big matrix K. Okay, that's a long story. Let me not write the mathematics, but let's for now agree that the total amount of unrest will be what we can call a Dirichlet energy, which is some form of an integral or sum of all of these local unrests, right? I can actually work it out for a graph, representation. And for a graph representation, I think that will be in this form of X for the displacement of the nodes transposed a matrix called the Laplacian matrix L and times X. So this is for the graphs, and I can explain that, but that falls much beyond the scope of this talk. Okay. So what does that have to do with this? So this, you could say, is this L is very similar to this matrix K. And this happens in higher dimensions when we have more than one element, but if you had only one element, this would end up being for one single element 1/2 of K x squared. That should remind you, I hope, from high school about the potential energy stored in a spring that you have squeezed for some amount X. So you cause some unrest in the spring. that means you also store some amount of energy. Does that pen have some spring in it? Maybe you can put it on the table and release that that amount of energy to let. No. Just as a pen. Ah, yes. Ah, yes. Yeah, you store the energy and then you release the energy, right? So it's proof that it is basically an energy storage. You know how useful that is. That's another step. A winding engine. Have you seen them? Like these toys that have a winding engine with a spring inside. You store some amount of energy and then you let it go, right? So how much is that energy? It's an integral, which is something that you might have forgotten completely about, of some force let me put it this way. It's an integral of an amount of work that you need to do through the trajectory of doing the job, right? And the amount of work that you do here will be basically a dot product. So this is what they told you in high school probably. So that the amount of work will be, I think, F x delta x. So this is the amount of work. Is that true? So it's an integral of a work over a trajectory. So this is the work. If you have to squeeze it this much, you have to overcome this much of force. So fx differential of x, the integral of this, right? And what will be the f? Yeah, you're right. Yeah. So it's the integral of force over the trajectory. Yeah. You're right. And this f is proportionate to the x. So it ends up being the integral of kx differential of x, which is about finding a function whose derivative has this form. What would be that function? 1/2 of kx squared will exactly have this derivative. An integral is an antiderivative, right? So for one spring, this would be it. For a system of springs, it will take a form like this one. Yeah. And this is something that you can call the stiffness matrix. This is a very important form of an equation that is known as a quadratic form. It pops up again. X transpose kx. So k ends up being a square matrix. X is a vector. X transpose is also a vector, but now becomes a row vector. So what is the total amount is it going to be a vector, a matrix, or something else? So suppose this is going to be a square matrix, K, which shows the stiffness between every two nodes in the system, sort of. Exactly. So you have a square matrix of size n by n. You have a bunch of variables n by 1. So the result of this multiplication is going to be a vector of size n by 1. And this other one, which was x plus transpose, will be a vector 1 by n. The dot product of these two ends up being a single number, which is a total measure, a single number scalar, a total measure of unrest in the system. Yeah. The ways to form this matrix K are very much related to graph theory. That process of forming this matrix K is called an assembly process, which has to do with the connectivity between these nodes and the way we number them. And of course, the stiffness of the things in between those nodes, right? So this stiffness matrix, this equation, etc., gives us one picture of this. So this is another way of looking at this. So if we can say that this integral of force over a domain in a discrete form will exactly take this shape. U is the common notation for the displacement, especially along a degree of freedom. So U is the displacement, and this is a force. And do you know the notion of physical dimensionality for quantities? Never heard of it? Okay, I can quickly maybe mention it. So in physics, you are working with quantities that have different units, like electric current has a unit amperes. Electric difference in potential has a unit voltage, volt. Temperature has a unit like centigrade or Fahrenheit, degrees of centigrade or Fahrenheit, Celsius, or an absolute measure, Kelvin of temperature, etc., etc. So long story short, there are only 7 elemental quantities in physics: mass, length, time, absolute temperature, electric current, etc., etc. The other ones are, I don't know, illuminance, shown with something like J, etc. Not my cup of tea. LT. Okay. So and this amount of substance, mole. So there are 7 elemental quantities. Every other quantity in physics is a combination of these quantities. And I'm not talking about the units. I'm not talking about, for instance, joules and kilowatt hours and British thermal units for energy. These are all the different units describing the same kind of quantity, which is energy. Can be mechanical energy, can be the energy in food that we eat, that anything that is energy has that same dimensionality, which is the dimensionality of this, which is the dimensionality of force times something that has a dimensionality L. So what is the dimensionality of force? Let's call Sir Isaac Newton. So this is mass, obviously this has a dimension of mass, but what is acceleration? So meters per square seconds. So you can guess that that will be meters, L, square second, so that's of dimension time, but at the bottom, at the denominator of the fraction. So that will be LT to the -2. And so force will be MLT to the -2. That's clear, right? And therefore energy will be ML squared T to the -2. That's the dimensionality of energy. So you already see that this has the same dimensionality. These quantities, whatever they are force. These quantities, whatever they are, they're a displacement. Well, in this case, the sort of energy that we want to minimize happens to be actually mechanical energy. We can call it also the strain energy in the system. Because what is this energy? Where does this even come from? This comes from adding all the, so this was the exerted force, and this is this is a vector showing all the compliances or the strains that the system has gone through given this exerted vector forces. So what is compliance? If I do this on this table, see what happens? The table complies a little bit with my force of weight, right? You're sitting on a chair. This chair has some cushion, and the cushion has complied to the force, or has strained a lot, visibly a lot under your force, right? And basically, most materials around us have that sort of behavior, but for many materials, that's not very visible. But for some materials, we can actually see that. Actually, in control systems engineering, we had a course about sensors. There are sensors that can even measure the amount of strain on this thing. When we push it, it actually strains, right? So you can think of most of the stuff around you as the springs, right? You push them, they strain, and there are sensors that can even measure that amount of strain, which is not visible with bare eyes, right? But it does strain under that stress or pressure or force. Pressure and stress, by the way, have the same dimensionality, which is force divided over an area, right? So it's very important to be aware of these dimensionalities to prevent some very, very horrible mistakes, okay? Horrible mistakes like adding apples and oranges, like adding 2 euros to 2 meters and so on and so forth, right? So 2 plus 2 does not always equal to 4. In mathematics, it does. In physics, it doesn't necessarily make sense even, right? Multiplication is usually okay, because with multiplication and division, you can make new things, new quantities. In fact, you have these quantities combined together like M, L, T, K, A, etc., 7 of them, to these powers, alpha, beta, gamma, etc. Any quantity in physics that you see around you can be actually described in terms of some combination of these elemental quantities, but never an addition or subtraction or average, because those stuff would mean that you are actually comparing apples and oranges. What is the meaning of 2 euros plus 2 meters? What is the meaning of 2 euros plus 2 meters? Yeah, it is laughable, but I see many people, some of them even with a PhD degree, doing that, and they're not even bothered by it. They're doing it happily and for decision making even. They say meters are more important than euros, or euros are more important than meters. You know, so that's why I usually make a couple of statements about this. So anyway, back to this business. So F, whether transpose or not. So at the end, this ends up being a number again. So this is a vector of forces over all the degrees of freedoms or nodes, if these are nodal displacements. And these are all the displacements corresponding to the nodes. Let's say for the nodes, not degrees of freedom for now. Keep this simple. And then again, you have a sum, basically. What a horrible sigma. Sum of F of I, U of I. This actually means that, right? So it's a sum of the total amount of unrest in the system. There was a force, there was a compliance. There was a force, there was a compliance. There was a force, there was a compliance. What is the total amount of compliance? That's total sum of all of these, which is encapsulated beautifully into this form, right? You can, it's also tempting to think about it in this way, which is that this F has something to do with the displacement, right? What is the relation? The relation is that there is going to be a big matrix K. This one actually shows the assembly procedure for the matrix K. Times a vector U, let's indicate vectors like this and matrices like this, that will be another vector F. Yeah. So maybe I can substitute this part into this equation and look at it in this light. So, and for decorative reasons, I prefer to actually write this as U transpose F. If you don't mind, it will be like tomato and tomato for our purposes. So I'm now going to replace F with this. So it will be, long story short, U transpose K U. And usually we differentiate them with lowercase and uppercase. So uppercase is reserved for matrices, uppercase bold, and lowercase and bold is for vectors. So this one will be some value C that we can call compliance, because we just established the fact that a form in a matrix equation in this form, which we call a quadratic form, actually ends up being a single scalar number. This is a square matrix. This is a vector. This is a vector of appropriate dimensions, so they can be multiplied together, and it ends up being one single number. Remember, right? That single number is the integral, or the, in this case, the Dirichlet energy or the strain energy, right? But you remember what I told you about the decision variable and the fundamental problem being that the question should be reduced or converted to a series of questions in the form of to be or not to be questions for every single element in our system. So where are the elements? The elements are typically given as these x sub I values together in a vector like n by 1. And this vector is a member of this vector space of some values in this form, some x minimum to 1, let's say, being a relative notion of density. And I already told you why we don't start from 0, but for decorative purposes, you can think of it as 0 to the power of n. And this power is not power, it's the Cartesian product, right? So this is a fancy way of saying that these are going to be vectors like this long, n by 1. Each entry of which will actually be a number in the range of x minimum and 1. Yeah, tuples of vectors. But because there are connections between them, there are operations that can operate on these tuples. Instead of tuples, we call them vectors. But this notation is common, right? So these are the x values, right? So what can possibly have something to do with these decision variables in this equation? What would be your first guess? What could be? Our goal, therefore, let me recapitulate our goal. Our goal is to make this as a function of the decision variable. Otherwise, how can we tell if we are making things better or worse? What was the question? The to be or not to be question for every single element. If you don't have any good reason to remove something or add something back, I wouldn't go as far as saying that we are operating like that monkey behind the typewriter, but okay, we are to some extent lost if you don't have a good reason, if you don't have a good numerical reason to do so, right? If we want to have that reason, first we should be able to evaluate. Does it even get better if I do this or not, right? So the removal of each of these elements in this formulation is going to make it better, definitely better. But which one to be removed, that's another question, which is going to be the gradient of this with respect to, or the sensitivity of this with respect to each and every one of those decision variables, which is shown as the gradient of this with this sign, which is called nabla. This is the gradient operator, which basically produces a long vector of partial derivatives of this with respect to x0, with respect to x1, etc., partial derivative of the compliance with respect to x n minus 1, transposed. Vectors by default are column vectors. If we write them as row vectors, we put the transpose sign to indicate that the default is the column vector, right? So why should we do this? Suppose you go home and you see a UFO, an unidentified flying object from a bunch of aliens landed on your backyard, and they're doing crazy things at your home, and you want to escape the whole situation. And apparently there's some sort of a doomsday, and you want to be smart and you want to fly with the UFO of the aliens to somewhere else, escape the situation. You go into the UFO, you see a bunch of levers and knobs and buttons on the control panel of the UFO. What's the first thing you do? Do you try to push like 10 buttons at the same time and play with a few things at the same time? You will probably try to nudge one of the levers a little bit, see what happens. Does it move a little bit like that? Or something opens a door, etc. So you start nudging them little by little, figuring out which one does what, right? That's the meaning of taking partial derivatives, right? Okay. And if you take all these partial derivatives, then you have a good idea about sensitivity of the thing that you care about with respect to the decision variables. So the decision variables are these to be or not to be decisions about each and every one of those elements, right? Okay, so where were we? Okay, so these decision variables, if they don't have any effect on whatever we're doing here, then why are we even computing this? So when we say evaluation function, evaluation of what exactly? We should be evaluating one of the many possible configurations in our system, one of the many possible topologies in our system. Configuration, topology, layout, these are almost interchangeable in this context. And each configuration corresponds to one subgraph in that supergraph, the links of which are already present, right? So the only question is which node should be included or not, right? But which node or which element, if the node equals the element, which element to be included? Well, actually, you're looking at the answer to my question on the screen. Which node included or not included, that will actually change this graph for which you can write the big stiffness matrix. Imagine this graph for the sake of this presentation is just constructed out of these one-dimensional elements which are working like springs in between these nodes, right? So the stiffness, the big stiffness matrix of this system can now depend only on having or not having this node or not, or not, right? Having or not having each and every one of these nodes. Why? Because that big K matrix is already assembled by putting together the stiffnesses of corresponding to the elements. I'm cheating a little bit in the notation here because the elements are here, the springs, and not the nodes, but nevertheless, it's similar to that, right? So long story short, what can we expect to be dependent on the decision variable here? K, yeah. So K effectively is a function of our decision variable, X. So a tricky question, can can we say that compliance is the opposite of stiffness? Because for a single spring, it kind of makes sense. So if something is really stiff, it does not comply so much with the force. It does not strain. So that's our notion of stiffness, the intuitive notion. But this definition of compliance is not exactly the opposite of stiffness. It's not the inverse or the opposite, or it's this. This is compliance, right? But colloquially or informally, you can say that, okay, by minimizing the compliance, you are kind of, loosely speaking, you're kind of maximizing the rigidity of the system. And in doing so, you are actually removing nodes from that massive block. So that's another thing, that's another line along which our work kind of differs from this typical structural topology optimization, because minimizing that mass is not our biggest problem. We don't want to minimize that mass, that amount of mass. As soon as we reach the valid level, then it should be fine, right? Target, yeah. So up to a certain level. So because if you don't have that constraint, this will disappear, right? We will worry about it when the algorithm is running. I have no number in my mind. But yeah, so you want to make it less massive, of course, because that means more efficient, etc., more elegant. If we want to see something, then we have to go below the volume that is already there. Otherwise, the very first one is also a design, right? Put the entire bulk of mass over there, right? That is also a design. And that's something that many designers actually do. They make very bulky, heavy things because they're very expressive, according to them. Yeah. But then that's exactly the thing that happens with these things that we take for granted, like the floor slabs of buildings. They cover the entire. So if you compare them with this business, you have these very thick floor slabs in buildings covering this entire shape. Who said they should look like this? Should I say, may he rest in peace, Le Corbusier, right? Or someone thought this is very efficient. Efficient for whom? Efficient, yes, efficient, yeah. For production, this is efficient. For the planet, this is a crime because this is a gigantic amount of concrete and a lot of rebars, steel rebars, for dealing with the tensions here. Because this is basically an element working in bending. What could this have been? Something like this, maybe. Right? To be a little bit more reasonable with respect to the load case and the forces. And imagine, okay, if it's one building, the next building, but if it's 1 million buildings, like 1 million homes, then this is a big deal. It's a huge amount of embodied carbon in these materials. Huge, right? So this is one of the things, one of the reasons why I say the Gothic architecture from the so-called Dark Ages is more advanced than our architecture in these modern times, right? You don't have that there because people accepted the constraints of not having, they did have steel, but they did not have so much of it. It's not something you could go to a shop and buy and talk to a mayor and get whatever amount of budget you want to have and just buy as much as you want, right? Back to that description of engineering if you have unlimited resources and anybody can make something that's not engineering, right? So we want to make it efficient, reducing the amount of mass, but here we don't directly reduce the amount of mass, we reduce the amount of compliance, but effectively in the process, because we're removing these nodal elements, we are also effectively reducing the amount of mass up to a certain level before the whole thing disappears, right? Okay. And so a couple of things about notation. So they usually typically assume that the stiffness of every single element is based on some density value like rho of the element in question. And that element, if it had the full density, which is 1, between 0 and 1, or between the minimum density and maximum density, then it would have such a stiffness matrix. One pixel-like element would correspond to a little stiffness matrix here in the form of minus k something, blah, blah, blah. So this is for the ith, jth, and I don't know, kth and lth nodes that it connects to. Some form of a matrix in the middle of a much bigger matrix. That is the assembly procedure. And this is a matrix, all of whose items are 0, except for this bunch of stiffnesses between these degrees of freedom or these nodes. And then you add them here. You basically add these pictures that have only a few elements in them. And then when you have added them all together, then you get the stiffness matrix, the big stiffness matrix for the whole picture. That is the most important part of a finite element modeling procedure, the assembly of the stiffness matrix, right? Yeah, so this big thing here is actually the big K, this whole thing. So this means subject to, this means minimize this for these two arguments. So U is apparently considered to be an argument, but the real decision variable here is this vector decision variables describing the density of the materials in there. Because if you remember, I told you that it's not just to be or not to be. It can be about the halo of the shape. So we allow these densities to range between 0 and 1, or some minimum density to 1, like this, to make it more numerically stable and numerically pleasant for an optimization algorithm that we are going to use at the end for solving this problem. And most of the papers in this line of work, they use one optimization algorithm that is called the method of moving asymptotes, which is written by a Swede mathematician. I've forgotten his name, but anyway. So the solver of this problem is not your concern. The solver of this problem is going to be a standard solver that you use. The formulation of this is your concern. How do we get to this format, right? And there's another one that's, I've forgotten the name, but anyhow. Then this is also our constraint. So subject to usually lists all the constraints. So this is one constraint, which is basically the finite element equation, KU equals F. This is our simulation. This is our constraint of volumetric constraint, or the mass constraint, because volume multiplied by density equals mass, right? So volume multiplied by density, sum of all volume elements multiplied by density of the same element, summed up over all of the possible elements in the system, that gives you the total volume of that particular design, which is supposed to be less than or equal to the minimum acceptable volume, or the maximum acceptable. But you typically stop exactly at that point. You don't go lower. Yeah. And how do you choose which elements to kick out or set to the minimum density from these sensitivities? That's the big picture of at least this type of topology optimization, but you can also think about the bigger picture, which is that you have to have such a cost function, some cost as a function of decision variables. These decision variables correspond to the elements in your topology, in the supergraph. And these are either like Boolean variables, to be or not to be questions, or float variables between 0 and 1, sort of density variables. And then all we need to have is a notion that there is an evaluation that we can do that can show us the dependence of the decision variables and the cost or some form of energy that we care about, the EVO energy, the annoying thing that we want to minimize, right? Or it can also be a benefit that we want to maximize. That's also possible, right? So an optimization problem is either a minimization problem or maximization problem. Of what? That's the big question, right? And then what can we do about it? It's the decision variables. We can set them in a particular way, and that particular way is our design, right? So effectively, by solving such an optimization problem, by looking at these gradients, we can pick up the one that's whose removal, if it has a high effect on the cost, that means the removal of that one will actually yield the most improvement. So at every iteration, the one that has the highest effect on the cost is the one that has the highest such partial derivative. If you were to remove one, or I don't know, top 5 from the bottom, like the worst ones, the biggest ones, then we could remove this one. Again, I'm oversimplifying the process, but that's a general idea, right? You remove those and things get better, right? Then you go to the next iteration. What has changed in the next iteration? Your stiffness has changed because now you don't have those elements that you had before. So you recompute this or you remove these elements from the big, you basically need to update this. Well, let's say in general, you need to update this evaluation function. In this case, you need to update this stiffness. In another case, you need to update your evaluation function given the new topology, right? Shall we call it a day at this point? Time is it? Not so bad. Okay, so questions? Burning questions? Okay.
I think there's a lot to take in. I'm already sitting here and I'm like, yeah, I will definitely be rewatching this again. So,
Okay. So yeah, some things to think about in the weekend, right? So I hope you enjoyed it. So I stop the recording if there is no question. Yeah.